So, welcome everyone to this week's Origins colloquium, which is attached to the Planet Formation and Exoplanet Evolution workshop. So, it's a great pleasure to welcome Giovanna Tinetti to give the talk today. Giovanna received a PhD from University of Turin and was in theoretical physics, a PhD. She was then, she's been a postdoctoral researcher at the Jet Propulsion Laboratory in California, and part of the NASA Astrobiology Institute. She was at IAP in Paris as an ESA fellow, and one of her research achievements at the time was first to detect water in an exoplanet beyond the solar system. Giovanna has been faculty at University College London, but last year, 2 years ago, has joined King's College London. As the PI of the Ariel mission, and we're going to hear about some of that now. Yeah, welcome, Giovanna.
Thank you so much, Jonathan, for this great opportunity to present at this colloquium, and it's great to see in the room many people that I know because of Ariel, because of exoplanets, and so it's really a fantastic opportunity for me to discuss with all of you what's going on in this field. I'm trying to see if I can change the slide.
Just click once.
Okay. Okay, here we are. So just to set the scene, planets are everywhere. This is something that we have learned recently. Statistically speaking, we're expecting to have at least as many planets as stars, billions in our galaxy alone. But the counting at the moment is more than 6,000, is not yet billions, which means that there is a lot of efforts that the entire community is doing on one end to increase the number of exoplanets that are known, but I think also to try to understand much better what is the exoplanet demographics. Because if you're looking at plots, at least one that I'm sure many of you are familiar with, on one end we can see straight that the solar system planets are not really representative of what we are seeing out there. There is a much greater diversity. But at the same time, we're still missing a lot of planets in this part of the diagram. And most probably, these are planets that we're missing, not because they're not necessarily there, but simply because of the detection limitations that we currently have. But I think we have a lot of opportunities, in particular in the next 5 to 10 years, because of a number in particular space missions. Gaia will have the new release by the end of this year. The expectation is to have thousands of planets being discovered with the astrometric technique. Plato, as we heard before, to be launched in January 2027. The Nancy Roman Space Telescope, and from China, the Earth 2.0. All these missions will have different techniques here, microlensing, transit, and astrometry, but all of them together will probably deliver many planets in this region that at the moment we are completely missing. And perhaps almost most importantly, if we're looking at the planets that are observed so far and discovered so far through a combination of space missions and ground-based facilities, we are still, with the exception of microlensing, really restricted into the solar neighborhood. And we don't know so much how the statistic is changing in different places of the galaxy. But because of these space missions that I mentioned before, many of those will have a higher sensitivity to other regions of the galaxy. So perhaps we will see different type of distributions and populations in different parts. And so to me, there is really an exceptional moment in time to understand better the exoplanet demographics going forward. At the moment, the statistic we have is still very biased towards what we have learned through transit and radial velocity, because these are the most successful technique. And if we're looking at planets that are relatively close to the star, less than 100 days period, then what we learned, in particular thanks to the statistics of Kepler, is that we're seeing this, I'm sure you're all aware about this bimodal, where we have two peaks. On one end, we learned that small planets seem to be more numerous than the bigger one, something that nobody knew before Kepler or other detections were made. But also this bimodal that is quite puzzling, in particular this peak here in between the size of the Earth and the size of Neptune is suggestive of having many planets that are in between the Earth and Neptune. Are they super Earth? Are they some Neptune? Are a mix of those? What is their composition? Clearly, in particular, this paper and many others that followed has opened so many questions about the composition of these intermediate planets between the Earth and Neptune, but also how these planets are forming. Because, and this clearly is a question that many people in this audience are very actively working on, because the fact that we're seeing so many of them, and the fact that we don't have them in our own solar system, is really opening so many questions about the formation of planets, how the environment is shaping them. And so this is clearly very active research, and we've heard already other talks before me really pointed out that the many activities are going on to try to understand all this. We shouldn't forget the star. In particular, there is a entire literature that is suggesting that this bimodal distribution might only be partially caused by the formation, but we should look at the star and the star having a very important role, in particular in the early moment of the formation of planetary system, where the stars are more active. And the fact that in particular from observations, we are seeing some changes in where the gap is located, depending on the type of star, that is suggestive that the star has a big role. And again, understanding even better what exactly is this role is something as a community we need to follow. Now, my interest throughout the years has been focused and is still focused quite a lot on atmospheric composition of exoplanets. And this is because I think in addition to many of the parameters that I mentioned so far, it can really tell us something about something more about the nature of the planet, the history of the planet. And although, of course, disentangling all the physical and chemical processes that are going on during the history and formation of an exoplanet, it's impossible to do all that when you have just a limited number of exoplanet atmosphere observed. The hope that we all have is that if we have a very large number of exoplanet atmosphere being detected and understood, then we might understand, because of these populations, something more about all these physical and chemical processes that must be behind the formation and history of all exoplanets. We are clearly not there yet, but I think it's almost science fiction that we have nowadays many different techniques to detect the composition and structure of exoplanet atmospheres. This is definitely something that when I started to work on exoplanet, it was science fiction. And the fact that nowadays you have transit direct imaging, high dispersion spectroscopy from the ground, all coming in with very complementary information is really fantastic, because it really allows us to be much more specific about the questions that we're asking. And I think that the more we are progressing in the field of exoplanet atmosphere, the more I think we're realizing that perhaps a little bit like detection, one technique only sometimes is not enough to extract conclusively some information. Most of the time, you might want to have at least two techniques that are confirming some detections. So in a certain sense, we're evolving towards what are already the methodology that the entire community is doing when it comes to detection. What I mean by that? Well, I will explain through some slides how, in particular, space-based observations, in particular when it comes to transit, and ground-based or high resolution are really complementary, but using synergy can provide a really fantastic opportunity really to understand better what's going on. But also, again, direct imaging and transit are typically looking at very different type of planets. And so they are giving us a different information in terms of planetary type. So When it comes to transit spectroscopy, and in particular the use of infrared to extract molecular composition of exoplanets, the start was really through Hubble and Spitzer. And back then, the data were extremely sparse, with a lot of question marks because of the analysis techniques that we were all trying. We're all pushing this telescope to go well beyond what were the capabilities. And clearly, in doing that, we're all conscious of the fact that we were potentially extracting things that were not entirely correct. But that's how it started. And in particular, we were trying to put together multiple data sets, data points that were typically taken at different time with different instruments. And all these instruments were never really calibrated to the level of the few part per millions that you know in order to do that. Stellar activity was not something that we were considering so intrinsically as part of the problem. So clearly that was the start. But understanding all these challenges, I think it really gave the community also the possibility to evolve and to improve, both in terms of techniques, but also in terms of approaches. And I see in the room Giuseppe Morello. He has really fought against the systematics throughout his careers. In particular, I still remember Giuseppe when he did his master thesis on some Spitzer data that had all sorts of systematic, really, really brutal systematics. And he was able, for instance, to use independent components analysis to correlate some of the information at the level of pixel to solve one problem that was concerning the infrared detector. And so clearly back then we were all trying things in order to see if we could disentangle all the systematics from the signal. And so I think my team at UCL and later on at King's, we really started to use a lot of this machine learning technique out of trying to find other methods to get rid of stellar activity or correct for instrument systems. And many of these activities are working. Of course, there is a lot of work because it's not just one specific technique that is working. It really depends on the systematic. It really depends what you're trying to do. So there is a lot of work behind the scene that is needed. And we also try to push as much as we could on population studies. And so if the analysis of one planet is perhaps not as conclusive as I would like, what happens if you're combining together many tens of planets? And in a certain sense, recently, if you go to the archives of Hubble and Spitzer, you start to see really tens, in particular cases, atmosphere that have been analyzed with the two telescopes. And so you can really do a lot of digging into this archive and try population studies. Throughout all the studies, we weren't necessarily able to push beyond what is already understood at the level of individual planets, so that most of the time water vapor is there. In many of these gas giant planets, there is water, and some other molecule have been suggested, but clearly always in a way that is not necessarily so conclusive. And this is because, again, Hubble and Spitzer were not ideal for doing this kind of work. Certainly, throughout this journey, we also try to push as much as possible our data models open. So really pushing for open science, open source models. And I'm really pleased that nowadays all the community is actually doing that as a standard routine. But a few years ago was perhaps not necessarily the way that most of the community was reacting. And so I'm quite happy to see that the push for making sure that we're all more transparent with our data and our model has driven some of the effort really to be as open as possible in the community. Again, in this journey, we have all understood the line list. So the quantum information about the transitions for molecule, for atoms, for ions is super important. If you don't know well where the transitions are, it's garbage in, garbage out in the models that we are using to interpret this data. And unfortunately, again, going back to when it started to work in this field, there weren't many line lists, in particular hot temperature. Most of the line lists that were available were at room temperature because they were used for the Earth atmosphere for obvious reasons. And so throughout the year, in particular, the ExoMol team at UCL, through Jonathan Tennyson and Sergei Yurchenko, done an amazing work really to calculate ab initio a lot of these line lists at different temperature for many of the molecules that the entire community now is using, and really working with experimentalists to be better and better in terms of, in particular, line position. Because from ab initio, you can do very well the intensity, but the line position needs a lot of iteration with experimentalists. And for high resolution spectroscopy, that's where the line position is important. More recently, this is a work done by a PhD student working between London and Lisbon, Rafael Ranco Silva. He's used, on the contrary, some data from the ground about Titan to extract a high-resolution line list for methane, which is really not so well known. And this new line list hopefully will help even more some of the optical observations for solar system objects, but also later on for exoplanets. Moving to Webb. Webb has been transformational in the field because all of a sudden, the signal to noise compared to what we were able to do with Hubble or Spitzer is different order of magnitude. But not only is the wavelength range that all of a sudden it became available to the community that was mind-blowing. Instead of being restricted to photometric bands, and in particular when it comes to Hubble, near infrared or visible or UV, really opening up to the mid infrared in a massive way has been absolutely fantastic for all of us. The data are so good that in my view now is the community that needs to step up in terms of model that are good enough to interpret this data. And clearly, we all are struggling with how good are these data and how more precise and more accurate we need to be with the models that we're using. And so to me, there is still a lot of space, despite the fact a lot of this data are already been published in many ways. There is space really to still push how much we can still extract, because perhaps not everything is so conclusive. And so I'm using here the example of WASP-39b, which is one of the most published and studied planets. And we did a more recent analysis led by Sushan Ma at King's. So what she's been doing is to basically use all the data from Webb, from all the instrumentation, and try to, as much as possible, interpret them all together. And there is also, in the case of Webb, although it's less dramatic compared to Hubble and Spitzer, still this problem of drift, because not always the instruments are really overlapping. And so there is still some bit of a question mark there. But still, and what Sushan in her work has suggested is that there is a way to explain, in particular, the more SO2 absorption and some of the sulfur-bearing molecules that were interpreted earlier in a slightly different way, using more a combination of silicon-bearing molecules and clouds. Now, we're not suggesting that SO2 is incorrect and we are right. We are just saying there is a different way an alternative way to interpret the data. So this means that perhaps we should all try to push a little bit more how much we can extract out of the data, and whether there is a way also to confirm whether it's SAO or SO2 in a different way, because at the moment, some of this interpretation are not necessarily unique. And the fact that, for instance, there are alternative techniques also using Webb at high resolution. This is a paper that was led by Emma Esparza-Borges, looking at high resolution data with Webb. I think in this particular paper for WASP-39b, she was able to confirm water, CO2, and CO, but not necessarily the other minor species. And so again, it's still a little bit open how we interpret them. But certainly the analysis and detections from the ground are super important, again, maybe to make sure that we're really seeing a specific molecule or not. In particular, when we're talking about molecules that are hard to be detected from space because they either have a transition that is hard to pick up, like CO from space data, or very sharp line that even Webb sometimes cannot necessarily detect them. So this is to say that I think going forward, we have the interest really of pushing several techniques from the ground and from space and observation in order to make sure of what we're really seeing, because I think it's really important going forward. Webb has opened up the ability not only to focus on giant planets or Neptunes, which was more what Spitz and Hubble were doing, but also to push for small planets and in some cases even temperate one, like the case of K2-18b. This is certainly one of the most studied super Earths of Neptune. And clearly there is a lot of work in the literature trying to interpret data from the past, but also from, in particular, from Webb. And I think this data confirming methane being present, argon being present, and there were really a lot of debates about the suggestion of biosignature. I don't think the data are probably uniquely interpretable in a way that one would straight go there. In a simpler way, we also looked a little bit at the new data for K2-18b, and this is a work that is led by Wan Liu, and putting together multiple data sets from all the instruments on Webb that looks at this particular planet. She has suggested through her interpretation that perhaps one has some hazes, more similar to what Titan hazes might look like. From a chemistry perspective, would make a lot of sense. There is another paper that is led by Panios Lavas that is looking at the physics behind that and at the consistency of this model. Again, also here you're seeing still relatively big error bars, and so the interpretation cannot be unique. And so that's where perhaps in this case we need to wait for the ELT probably to be really sure that some specific molecule might be there or not. This is a very faint star, and so probably even current instruments from the ground are struggling a little bit to get that. Just to remind everybody that the star is super important, and in particular, what we have done some years ago is to also look at a combination of data from STIS and WSC3 on Hubble. This is a work that was led by Rana Saba and Alex Thompson. And what they have found is that for the 20 attributors that they looked at, in many cases in the UV, so the STIS observations are showing a different basic response in the UV, which is suggestive of probably stellar activity. So if you don't remove stellar activity and you just take at face value how the spectrum it is, you are actually extracting interpretation for the temperature and for the water abundances that is incorrect. And so this is really, again, reminding all of us that the star is there and we need to do something about it. And of course, when it comes to even smaller planets and stars that are even more active, then the situation can be even more tricky. And this is not to forget stellar flares. They're there, and they can certainly contaminate from a spectral perspective some of the transit data, but also they can have a big impact in terms of chemical composition and also evolution of the atmosphere. And this is something that, as a community, again, we don't know so well because there are not tons of satellites in the X-rays, and not to speak about the UV. And most of the time, we're relying for the frequency in the visible. with tests on other similar satellites, but in the visible, you don't necessarily see the flaring signals or not as well. And so clearly, we are all struggling also to understand this part. Moving forward, I think in the next decades, I already mentioned some of the mission that will detect more planets and help with the demographics. I will spend a few words about Ariel, although I'm conscious that both online and here, many people are aware of Ariel, and so perhaps we can leave some of this to discussion. But then there are also many initiatives around the world and more to push for habitable world. And this is certainly fantastic, but I think, again, as a community, thinking about our shortcomings is super important. In particular, we want to make this leap towards something that is even more challenging going forward. Now, in terms of missions that will happen very soon, Ariel is expected to be launched in 2031, and we're talking about 1-meter class telescopes doing simultaneous coverage between 0.5 and 7.8 micron in the infrared. The simultaneous coverage is important because of all the reasons I was mentioning before. You don't want to try to assemble different instruments, knowing that is very hard, even when they overlap, to calibrate those instruments at the level that we need for the atmospheres. But also the stellar activity is something that is cautioning against trying to do observation in different time. The entire selling point of Ariel is really to go for a big population analysis of exoplanets. And so ideally, we want to cover around 1,000 exoplanets observed, different type of stars. And so really get a little bit of a chemical survey of exoplanets. Behind Ariel, there is a very large consortium that is including 16 ESA countries, contribution from NASA, JAXA, and Canadian Space Agency. Where are we in terms of payload and spacecraft? So we just finished the testing campaign around with the structure model that was shaken in all possible way. If you seem to see some of this on social media, there are some very fun videos showing some of the of this testing. And then we are going through many critical design reviews for many of the subsystems of the payload. And then when all this work will be done and everything is assembled for the flying model and retested as well, then everything will be sent to Airbus, which is the prime of the mission to be launched in 2031. Bexcoats, who is coordinating all our communication activities, has created this Ariel telescope on Link 3. So any of you who are interested in all our activities, it's all there. And in particular, we want to make sure that any of the work that the consortium is doing is really shared with the community at large, hopefully helping also some of our mission, our facilities, or in general, our studies of exoplanets. So you will see a lot of this there if you're interested in. We had an open conference in March 2026 at the ESA EXAT site in the UK, in front of where Ariel was tested. And we had more than 200 participants from all over the world. And that was really, really great because it was an opportunity for all of us in the consortium to get the feedback of the broader community and understand whether in the 5 years that we have to go, we are really well positioned in terms of work, preparatory work, and where we're heading. We still have some time to correct what we're doing if we need, but we really need to be well organized. And perhaps something that many of you in the audience or online might be interested in. We have an Ariel special issue that is being organized and will be published in RASTI, the RAST techniques and instruments. The deadline for submission of these manuscripts is the end of September this year. So if any of you is interested in publishing a paper that is Ariel related, it's open to the community. So you're absolutely most welcome. And here you have all the information, but even just go into the journal, you can see that. a lot of the work that currently is happening is around the target candidates of Ariel. And this is because on one end, we want to know what are the type of planets that we can rely on and then type of star to have a plan of how we want to execute all our observations. And this is the mission candidate sample, which again, openly available on GitHub and is maintained by Billy Edwards. But on the other end, we want to become more and more structured in the way that we have to monitor these parameters of this planet candidate, because we are becoming more and more aware that in many cases, some of the planetary, stellar, or orbital parameters are sometimes not really coherent with each other. We are getting them out of exoplanet catalogs from NASA or others. And in many cases, there is no scrutiny behind how they are related, whether they're consistent or not. And this is not something that we can afford when the mission is launched, because it means that we might lose efficiency in observations, we might have not good information. And so we need to make sure that the next 5 years we clean up as much as possible all this work. And we're relying on all the work in the consortium and many working groups and people to do that, but also to monitor better some of these parameters. In terms of science, on one end, among the key things that Ariel will try to achieve is to, through this chemical survey, understand whether there are some obvious transitions between one molecule or the other as a function of some of the stellar, planetary, and orbital parameters, or not. These are just simulations that the consortium is doing to see whether our observational strategy is consistent to be able to do something like this or not. But also there is a big push in the consortium and elsewhere to include more and more phase curves observations going up in terms of phase curves observed at the level of between 100 and 150 planets, because this is something that with a dedicated mission we can do more easily compared to general observatories like Webb, that for sure they're doing fabulous work, but you can't really necessarily always ask days of observation on Webb and for all the planets that we want. But also repetition through time. That's another thing that we can do, having the time in our hands. And these two strategies of observations are really good at looking at the complexity of planets that are complex in spatial way, but also in a time way, because they do change through time, both the planet and the star. Since there is a lot of interest in planet information, also, I will just mention that there is also a lot of work being done in the consortium to work out whether we can really extract the information that all people interested in information and elemental ratios in order to connect atmosphere with formation are extractable out of this data. And again, in an ideal world, probably yes, but of course, let's see what will be the data. And certainly a lot of work is also being done to look at the synergy Ariel and Webb. On one end, we're using Webb as much as we can to understand the complexity of these objects, to learn techniques, also to extract the signals, but also hopefully both these two facilities will fly together at a certain point. And so maybe we have an opportunity to use the two in a synergistic way, using Ariel for very bright sources and using time domain spectroscopy in a certain sense, and Webb following up at higher resolution and having a great sensitivity of a 6.5 meter telescope. So there's a lot that has been described in this in this paper that's been submitted to Rusty for the special issue, and you can find in AstroPH, so I'm not going to explain this now. Lots of work being done by the Ariel Stellar Characterization Working Group. They have an entire website with the stellar catalog, again, all openly available, and an opportunity to many of you, if you're interested in, to contribute and collaborate. Similarly, for a databases, whether it is line list or chemical reactions or cloud and haze optical parameters, all super important in order to look at this data. And although this database for Ariel and it has been conceived for Ariel. It can actually serve Webb or any other facilities that is looking into exoplanet atmospheric chemistry. I would just very briefly mention the challenges using AI to solve a number of problems that Ariel, like any other facility, may have. And I know that Katya is online, and so she's been certainly one of the biggest participant and winner in the past to many of these data challenges. The data challenge in 2025 in particular was again sponsored by Kaggle with a $50,000 prize. And so clearly this annual event is becoming more and more popular also in the community of machine learning and AI experts. Just a couple of words about ExoClock and the incredible work they have been doing throughout the years, bringing along also amateur astronomers to help us refining ephemerides of the planets of Ariel, showcasing how we really need the help of everybody. And I'm conscious of time, so I will just spend a couple of minutes to say that in addition to missions like Ariel and Webb, and clearly this is the focus of today's meeting, I think it's important to consider a bit of an ecosystem of facilities from ground and space, in particular when it comes to data that you don't necessarily need to have big facilities. And with this in mind, we have founded Blue Sky Space with some of our colleagues back then at UCL. And Blue Sky Space now is a scale-up company. And our idea is to find a commercial approach to be able to deliver more space science data to the global community. We have our first satellites operating now. It's called MOV. It was launched in November of last year. And MOV is basically looking at it's monitoring through time active stars, in particular to capture flaring activities. MOV is looking at spectrophotometry between 200 nanometer and 700 nanometer, so near UV to the visible. This is the first slide that we had in February, but we have a paper under review at the moment that hopefully we should be out soon with a lot of data and looking at, showing to the community the capabilities of this small satellite. And we have a lot of our ambitions to launch our satellite soon. Twinkle, which has been such a satellite I've been studying for a number of years, MOV Plus, a follow-up of MOV, and Radio Luna, which is a mission for a swarm of small satellite around the moon for cosmological observations. Let me wrap up to conclusion here. Have planets everywhere. Number of planets is increasing. Demographics is also improving thanks to a number of facilities from space and the ground. I think it's an incredible moment to really work in this field. When it comes to atmosphere, I think it's great that we have a number of techniques and also facilities from ground and space really to start delivering the kind of information that we need. But looking at the future, I think Ariel will, in addition to what is existing, we really make a big boost because of the capabilities to go for large number of statistical exoplanet atmospheres that combined with ground and Webb, I think will be really super important to understand this chemical sort of behavior of exoplanets when you start to play around with the many parameters of stars and planets and orbital configuration. And hopefully all this will tell us a bit more about the big picture of exoplanet formation and history. And more in general, I also want to make the point that although we have these fantastic facilities, and I mentioned many of those throughout my talk, in particular the very large one, we should keep our small facilities from ground and space because you need to help the understanding of what we're extracting out of Webb or Ariel or whatever, and using a lot of monitoring, whether it is for the star, whether it is to understand the mass of the planet, or any other stellar, planetary, and orbital parameter that are really, really important if we need to have a very precise interpretation of these objects. And with that, I thank you. And maybe there are some questions, but thank you very much for your attention and time.
Thanks very much. Any questions and discussions? So again, online, raise your hand. And if the Virginia room is there, somebody can help me there. Let's see then. So we can start here. I'd like to, normally we try and structure the discussion a little bit, but so we can focus on the science of atmospheres. There's the Ariel, maybe questions particularly on Ariel, but let's just see where we go here. Let's start with Jens.
Yeah, thank you, Giovanni. Great talk. I think it's slide 16. There you show a nice spectrum of WASP-39b. There's all these different instruments stitched together to get your whole spectrum from the optical to the 10 plus microns. Sorry, it's all the way in the beginning. Yeah, that one. The next one. The next slide.
Okay. This one.
Yeah.
Yeah.
So I think the spectrum is really cool. One thing that stands out to me really, really clearly is around 10 microns. You have this reduction of transit radius far underneath the continuum that you have elsewhere. I was wondering if is that real, or is there some sort of stitching that happens where the instruments may not be calibrated? And
Which one?
Yeah, the big bump downwards all the way to the right at 10 micron.
Okay, so yeah.
Yeah, that thing.
Yeah.
That thing that goes like several scale heights underneath the continuum elsewhere, right?
Mm-hmm.
Is that real? And B, what do you like? Why is that?
Okay, so in our paper we cited some of the suggestions that came also in the literature that is suggesting that one should probably avoid wavelengths beyond I think it was 11 or 12, I can't remember, because there seems to be potentially a contamination, possibly from dust in the disk on those wavelengths. Whether that is true or not is a question mark. But so we said that it's certainly hard for us to fit the data, but it's not the only one. But I think there is a suggestion that perhaps one should be careful in interpreting for this particular planet data beyond a certain wavelength. I think in the paper we are also citing the article that had that analysis more in depth.
Can I expand on this more generally? So given the quality of this data from Webb on these kinds of big planets, what would you say are the main open questions here then that, or surprises that people are coming across?
So to me, Webb again, absolutely fabulous and order of magnitude better than what we had before. But at the same time, when you're trying to detect minor species, and for minor species, I mean species that are not as abundant, or maybe they have just one transition, and then it's hard at low resolution. Yeah, and so I'm considering this low resolution, for instance, compared to the work that was done by Emma using cross correlation, a high resolution of Webb. And so at low resolution, and again, it's much higher resolution compared to the past, but still, you still have sometimes non-unique interpretation. So this is what the point we were trying to make in this particular paper, that sometimes you have multiple interpretation and they were equally fit. And things are complex, such as you quite rightly noticed that, this decrease in flux that could be due to something else. So on one end, sometimes being able to repeat some observations with Webb would definitely help, but also making sure that we try also with different instruments and different resolution, even for Webb, perhaps to confirm whether some of these minor species are really there, what abundance is, because these planets are complex. And so
how stable in time are these things? Is there any evidence for variability?
We don't know. We don't know. I mean, the expectation, of course, is that the stellar activity might be impacting mainly at the shorter wavelengths. down to the near infrared, but it is true that nobody ever did a full analysis of all wavelengths through time. And so open question, whether many of these atmospheres are variable in time, again, I don't think we have this answer. So to me, Webb really offers the opportunity to go to the next step in terms of challenging what are our assumptions so far, because I think that things are so good that really helps the entire community to push towards bigger questions.
Okay, Oliver.
Yeah, I actually had a question regarding MOV and MOV Plus, because that provides UV, or at least near UV, and especially for when Ariel is then flying in, well, early 30s, to characterize the stellar activity, simultaneous observations would be fantastic. So, but MOV probably is dead by then, most likely. Probably, or like is MOV Plus like planned?
MOV is relatively small satellite. We're talking about a 16-unit CubeSat, so we are not guaranteeing that MOV will be there with Ariel is flying, because we're talking about 2031.
Yes.
But MOV Plus could be, and I know that there are many other also satellites that community is also thinking. My point is definitely it looks like having information in the UV, it's helpful because the star is there.
Absolutely.
So the more we will be able to monitor the star even before Ariel is flying, even to understand what kind of objects we're dealing with.
But simultaneous would always be better.
Maybe, maybe not. I mean, what I'm trying to say here is perhaps we should, given that we have Webb now, let's already try with Webb. How far we can go in monitoring the star, in information on the star. To me, it's a huge opportunity that we have even before Ariel is flying. Sure.
Okay, Sadia.
Yeah, thank you so much, Tom. So I think you were talking about line lists, and you spoke about a couple of things that need iteration with experiments. I mean, how do you, I mean, what are those experiments? What do those experiments look like? And how do they account for like differences in terms of like the scales of the things that are happening?
Yeah, so thank you so much for your question. I think lab work, that's another dimension where I think the community should hopefully put more efforts, because on one end, the databases that I was mentioning before are including not just line lists, but many other optical parameters or chemical reaction and so on and so forth that at the moment are not really so well known. But to come back to your questions about the need for experiment for the position, this is particularly important for high resolution spectroscopy, because I think for Ariel, for low res Webb, let's say in that way, in a certain sense, the position is not as important, because you're operating at a resolution where you have quite a lot of broadening, in particular hot temperature for some of these molecules. So you can get away with not knowing your very precise position of your line. But ELTs, I mean, ELTs will not forgive anything, and even high resolution in general from the ground without necessarily running to the ELTs. That's where you really need an experiment, because the way the line lists are calculated, they need some iterations because they cannot be straight away precise on the line position. So they need to iterate with the experiment. And many of the experiments are tricky to be done, because not only they are a high temperature, and so you need to have a proper lab to do that, but some of the species are, not particularly easy to handle. And then there is also the broadening of the pressure, which is something that, again, we all avoiding a little bit to talk about, simply because it's so complicated and we don't know so well. But these are all things that when facilities are at the level of Webb and beyond, then I think we should try to think about all this, because it will all count.
Well, you mentioned the case of this SO2 and SIO.
SIO, yeah.
So can we summarize again?
Yes.
Are we able to distinguish between the two, or?
Well, in principle, yes, if you have enough resolution, but at the relatively low resolution of the spectrum, you have a way that is, from a Bayesian perspective, is not distinguishable, in particular, to explain the feature around the 4.1 micron has been a combination of SIO and other species as opposed to SO2. And then actually some of the features right here can be potentially explained by some silicate clouds. Again, one of the issues is that once you have clouds, and clearly there are clouds for this particular planet, because otherwise the continuum cannot be explained, then you don't know so well the optical properties, and the little we know about lab work in that sense is not always optimal. And so this is just to say that there is a lot of unknown, and I'm seeing this as an opportunity for all the community to try to step up, because I think we need to care about all the details now.
Well, then again, so there's a lot of interest in measuring, for example, C/O ratios or elemental ratios. So can you comment on, is that, are there too many degeneracies if you allow for clouds, or vertical stratification of abundances? What are your thoughts here?
At the moment, yes. So if you look at the spectrum like this, which is of the highest quality that we can ever imagine in terms of transfer spectroscopy from space, what the study is showing is that just have degeneracy, not in the presence of water or CO2, but when you're trying to pin down the actual abundances, then it does matter what the continuum is, what one species, how one species is abundant compared to another, whether you have clouds or hazes, and so on and so forth. And at the moment, if you just had this data, you would probably have some uncertainty on the elemental ratios. So that's where, in my view, is important as a community. We think about ways to decrease the degeneracy, and the only thing that I can think of is to come in with slightly different method, instrument, ground, space, and really pushing this question in different ways to get to something that is closer to what is the truth. So I'm not saying anything new compared to what people have been doing with solar system planets. I think perhaps as a community, we are being a little bit too optimistic that once the data are good, everything is solved. Possibly not. Many things are solved. Other things really needs a bit more work.
Well, we have about 5 minutes left for questions. Maybe we can have a few related to Ariel in particular. So remind me, it's a 4-year mission lifetime, but is there any wiggle room on that lifetime?
Completely. It's money. I mean, 4 years is not because of the cryogenic capabilities of Ariel are fading. It's not because the instrument should not last for long. Engineers are swearing that it can keep going. It's the cost of operations, the visa that are.
Yes, but once it's up there, how much does it cost per year to keep it going?
Well, some years ago, it was costing 10 million per year. Now, I think I think we have an interest as consortium community to make sure that in 4 years we are doing a bulk of science that is so relevant, is so good, and so transformational that we can then justify for an extension. And I think it's good that we're all focusing on this 4 years, because you never know with a space mission. You never know whether even you can reach 4 years. But said that, in principle, there's no showstopper from a technical perspective. And so one would hope that if we can demonstrate that the mission is working well, we'll have the possibility of having extensions.
But is there a technical lifetime?
No, technical lifetime in principle, it can keep going.
Okay, well,
maybe not forever, but long enough to do a lot more.
Yeah, well, it seems, given the cost of the mission, if it's just 10 million a year, we could have a whip round, and
well, one would hope, but as you know, we're living in moments in time where every penny is in astrophysics needs to be justified. So
okay. Ulrika.
Yes. maybe related to that, also to Ariel. So what is the plan for the target list? I mean, there is a candidate target list now, but how will it develop? Considering that Plato will launch soon, and there is
Absolutely.
other missions and projects could discover interesting targets.
Absolutely, it will keep evolving, but we need to make sure that, again, we're not necessarily relying on what might happen next and being completely unprepared in our way of, for instance, doing our scheduling, performance evaluation, or in our capability to follow up some of the targets and so on and so forth. So it's important that we have a plan. But then this plan can evolve and should evolve because, of course, we're expecting a lot of targets out of Plato, in particular, but other facilities from the ground and in space. So it's an evolving catalog, and that's why it is kept as an evolving catalog on the GitHub. And said that, we already know that we have perhaps a subset of these planets that are so bright that it's unlikely that we really want to get rid of those because they're ticking many boxes. But many of us, on the contrary, are good to have, but they're not necessarily so important and so critical that they shouldn't be questioned.
Mm-hmm. All right, Gopal, the question.
For the phase curve you're mentioning, so are you going to have in something in mind that what kind of candidate you are going? Are you going to repeat the candidate from the JWST list, or?
Okay, so there is also there a white paper that was submitted by the phase curve characterization working group. I think on one end, we certainly want to have, in particular during commissioning, some repetition of the work done by Webb, but more to calibrate that Ariel is functioning the correct way. But we don't necessarily want to repeat everything that would be probably silly. So there might be some overlaps, in particular for planets that are compatible also with Ariel, and that might be an opportunity also to evaluate temporal variability or other aspects for which with Webb there was not enough time or whatever is left to be done. But for sure, what Ariel we're not trying to do is to go for small and cold planets around M dwarf. That is really a regime that is quite unique to Webb. So Ariel will probably stay on very bright sources, probably hot planets or warm, small or large, but certainly around bright stars.
Mm-hmm. Very good then. Last quick question from Jens.
Yeah, it's a quick comment more than a quick question. You had one slide where you showed the expected signal for K2-18b with the ELT.
Mm-hmm. Is actually, I'm citing a work from...
yeah, this one.
Yeah.
So I'm actually the one who made this simulation.
Oh, okay. Okay. So you know exactly how in this plot.
I was actually going to comment on this. This is not a prediction of what Andes will see. Because it does not include a lot of noise.
Okay.
And so this is really a photon budget type of estimate rather than an actual prediction. Because I think in reality, also these high resolution spectrographs are very badly affected by your stellar activity and by your Rostov-Blofeld effect.
Okay.
So I'm afraid this is a very idealized case.
I see. But would you say that because the point I was trying to make, and I didn't necessarily spend too many words about, is for K2-18b, I think now it's clear that methane is there, other species are clearly there. But when it comes to the minor species that I was mentioning before, very hard to understand what's going on. There is a lot of degeneracy. And so my hope was that an instrument like Andes then it could be used to pin down whether there is C2A2 or what the carbon might be there in a way that from space, not even Webb is able to do.
I agree with that, with the caveat that this technique requires that the planet moves very rapidly. That's why there's a short period fantasy planet that is on that plot there.
Okay.
And that usually means that the planet is also very hot. And so a lot of those strange molecules you may not have in the regime where you can use this technique, where you have the velocity differential. The planet may then be so hot that your chemistry is no longer unknown or strange. So that may not always be the case, but that may be generated.
But we'll have time to discuss more at the
Yeah.
workshop.
Very interesting point. So thank you so much for pointing this out, and let's talk more so you can tell me what I should
Sure.
say, and this will do.
Okay, then we'll look. We've had a great talk and discussion. So let's thank Giovanna again.
Thank you.